Hey everyone, welcome back. We are going to do one of our last examples for chapter 17. We are back to our research example with the teenagers with high blood pressure, whose blood pressure would decrease if they took calcium supplements. Right, so we've changed our sample size to 100. It used to be 200. Just to kind of switch things up a little bit, but we are still assuming that 0.70 is the population proportion that would experience a decrease in blood pressure. And so we want to know what sample proportion would be required to be in the top 1% of all samples in this question or in this example. So the idea here, right, the thing that we're looking for here is we're given an area under the curve, right, to be in the top 1%. What's the sample proportion required? This is kind of like our missing value of interest question. So to solve this, it might be helpful to first draw a picture, right? Like always. We know that the average of all of our sample proportions is going to be equal to our population proportion, right, which is given here. And again, down here, we're told to assume 0.7 is the population proportion, right? So just like last time, our distribution of all of our sample proportions will be centered around 0.70. But we need to calculate the standard deviation, right, of our sample proportions, or our p-hats. And that's going to be equal to this 0.7 times 0.3, right? 1 minus, this 0.3 is 1 minus 0.7. And we need to divide by our sample size, right? And we don't want to forget to take the square root of all of this. So 0.7 times 0.3 is 0.21. If we divide 0.21 by 100, we just move our decimal place over 2 spots. So we get 0.0021. And we can't forget that square root, right? So now if we take the square root of 0.0021, we will get 0.0458, which I will round up to be 0.046. Okay. So now as we move from our mean up 1 standard deviation, we can add that 0.046 to our 0.70, get 0.746, add another 0.046, get 0.792. And then lastly, if we go up a third standard deviation, we'll get 0.838. Now, as we go down 1 standard deviation, we'll subtract 0.04 0.6 and get 0.654. If we go down a second standard deviation, we'll subtract another 0.046. We'll get to 0.0, whoops, not that. 0.608. And then if we go down our third standard deviation, subtract another 0.046, we'll get 0.562. Okay. And what are we looking for? We're looking for some cutoff p hat value, right? Some sample proportion where this area under the curve is exactly 1% to the right of us, right? So that this sample proportion that we get would be in the top 1% of all of our samples, right? So how can we do this? We can use our calculator with the inverse norm function that we've seen before. So let's just remember our standard deviation is 0.046. So I'll go ahead and switch over to our calculator so we can go to second and vars. And then we can go down to option 3, right? The inverse norm. INV norm is what we want to use when we're given the area under the curve and we're looking for one of those values along our x-axis. So we need to make sure we do 0.01, right, for 1%. The population mean that we were given was 0.70. And our standard deviation of our sample proportions was 0.046. And actually, I misspoke up here, right? We always have to put in the area under the curve to the left, right, for our inverse norm. So if we want to be in the top 1%, if we want 1% to our right, we have to take 1 minus what we're looking for, right? And so really, I need 0.99 of the area, or 99% of the area to the left. So I really should put 0.99 here. Now, if we just hit enter and enter, this tells us, right, that we need a sample proportion of 0.807 or 80.7% to be in the top 1% of these sample proportions. And that would be our answer, right? We could also use the Z formula, right? Where Z now is equal to P hat minus P over the standard deviation of our sample proportions. We're looking for this P hat, right? So we could have used a Z table to find 0.99 area under the curve to the left to find that missing Z value. And then just plugged in our population proportion here. That standard deviation of the sample proportions we calculated, right? And then we could have multiplied both sides, whatever this value is from the Z table, we would have found could multiply by 0.046, right, to cancel out. And then we could have added the 0.7 on both sides to be left with our p hat, and we should get something somewhat similar if we do it that way as well.